All right, hello, welcome back. If you're wondering where we're going, 6-2, 6-3 sometime this week. Next week, we'll see what happens. We will see what happens. But I expect this might take 2 lectures to get through 6-2, but we'll just see. We're gonna play it by ear. I got a timer up, so this thing is not gonna go past 35 minutes. I'm gonna endeavor to make sure that happens. If it does, I'll split it up into two. So we're talking today about discrete and continuous random variables. This is, it seems an innocuous title, but there's a lot in there, right? So we're talking about two pretty big topics, and these are things that don't show up on your formula sheet. So very first thing, we're gonna put a big old box around this in general. We're gonna come back to that and say eventually that's not on our formula sheet. These are things that aren't on our formula sheet, so they're challenging. What is this thing? This thing below is a linear transformation. How do you know that's a linear what does that even mean? A linear? Well, it's got a linear factor here. We have something to the first power. If you plotted that, it'd be a line, right? Depending on what x is, right? So linear transformations, adding or subtracting a constant a. We talked about what happens when we add a constant, plus a, plus minus. What does that do? It affects the center. Yes, the new center is the old center plus or minus a, and the shape and the spread are not changed. So adding only affects the center. However, for multiplying and dividing a constant, multiplying, dividing by b, that's going to affect both the center and the spread. So new center equals old center times b. Shape is not affected. Spread, new center, is old center. Oop, that's the spread. Times b. So the idea is that, well, what's the big idea? And this is something we saw in our chapter 2.5 test. Adding or subtracting affects the center. Multiplying and dividing affects both the center and the spread. How do we put that together in one formula? If we've got a random variable, if we have a random variable x, and x has mu of x and sigma x, and if y is a plus bx, then the mean of y, the new variable, is going to be that a plus b times the mean of x. That is, the center is affected by the adding and the multiplying, but the spread of this new variable is only affected by the multiplying. So that's one thing, the very first thing that needs to end up in some sort of box, highlighted, because that thing is not on your formula sheet. That is a linear transformation. How is the center and the spread affected by a linear transformation? The mean is affected by the adding and the multiplying. The spread is affected only by the multiplying. If you add the same value to every value in a data set, the spread has not changed. So that is our first formula. It needs to be on a note card. That is a linear transformation. That is something they do not give you. Excuse me. So let's jump into a question about the auto dealership. We saw this one before. We did it last time. We found the mean number of cars sold, and we found the standard deviation of cars sold. Let's do some reading here. So we remember that X was the number of cars sold during the first hour of business on a randomly selected Friday. That was something from last time that hopefully we remember. We found the mean and standard deviation of X using some formulas. The mean is the weighted average, multiplying the values times the probabilities. Standard deviation is a little more complicated. You've got a formula for it on your formula sheet. Number one, suppose, our favorite word. The dealership's manager received a $500 bonus for each car sold, all right? In addition, to encourage customers to buy cars on Friday mornings, the manager spends $75 to provide coffee and donuts. The manager's net profit T on a randomly selected Friday is the math word for equal sign, the bonus earned minus this 75. Find the mean and standard deviation of T. So the very first thing we need to do is say, well, what the hell is T? And how do we write T in terms of X? T has something to do with the number of cars that are sold. The amount of money this manager gets depends on how many cars he sells. All right. The net profit is the bonus earned minus this 75. Okay, so we get a $500 bonus for each car sold. How do I write that in terms of X? He gets $500 for each car he sells. 500X. And then what's he have to do? He has to spend some money on some donuts. If you wanted to, you could write a separate little distribution over to here to the side. Bonus and probability. Instead of cars sold and probability, think about this. Well, what's he going to do? If he sells 0 cars, he has lost $75. If he sells 1 car, 500 minus 75, 425. You can do this, 925 and 1425, and those probabilities would stay the same, 0.3, 0.4, 0.2, and 0.1. The spread, clearly, of money values is larger than the spread of cars he sells. No duh. And the bonus he gets is also clearly larger than the number of cars he sells. So we have this. So we could then find the mean of T and the standard deviation of T. Well, what's the thing here? The mean is affected by both the multiplying and the adding, but the spread is only affected by the multiplying. So it's going to be 500 mean of X minus 75. This is just going to be 500 standard deviation of X. You do that, what do you get? 1.1. So that becomes what, 550 minus 75. I think we get 475 there. And if we 0.943, 57 times 5, I don't know. Let's put in our calculator. Do I have a calculator? Yeah, I do. Maybe 500 times. And you get 417.5. Cool. 471.5, excuse me. All right, so what does this mean? This means that, you know, this is his long-term average bonus for Friday car sales. Which makes sense. If his mean number of cars sold was about 1.1, the mean amount of money he makes is going to be a little more than, you know, the transformation that goes along with 1. Makes sense. Cool. So again, you can check the key on these. I think there's a good key for these. So moving on, we're going to continue using these formulas right here for linear transformation. That's you take one thing, you're adding or multiplying it, but just one thing there. We're going to have a different case here in a moment. Let's take a look on the next page. Example, great. In a large introductory stats class, oh, how fun. The distribution X of raw scores, okay, X, raw scores on the test was approximately normally distributed with a mean of 17.2 and a standard deviation of 3.8. Great. Professor decides to scale the scores by multiplying the raw scores by 4 and adding 10. Okay. Define Y to be that scaled score. Find its mean and standard deviation. All right. So first thing we know X distributed normally with mean 17.2, standard deviation of 38. Oh, 3.8, excuse me. I'm going to put that as mean of X and sigma X over here. It's nice to have all that written down in a handy way. Professor decides to scale the scores by multiplying the raw scores by 4 and adding 10. All right, so we got Y equals 4X plus 10. Cool. find the mean and standard deviation of y. Okay, well, we can say, okay, mean of y then is 4 times the mean of x plus 10, because the mean is affected by multiplying and adding. What's that going to be? 4 times 17.2 plus 10. What is that? 4 times 17.2, 34, 68, 68.8, 78.8? I don't know. 4 times. Yeah, 78.8. So we've got the mean of 78.8. This is very much like what I do for you guys' test. Standard deviation of y is just going to be 4 sigma x, not affected by the adding. What's that going to give you? 4 times 3.8. 4 times 4 would be 16. 4 times 0.2 is 0.8. So that's going to be 15.2. So now we can say that y distributed normally, mean of 78.8, standard deviation 15.2. Again, very important that we can write all this stuff down with the notation. And then it asks us what's the probability that a student got a score greater than 90. From there, I'm going to leave it to you. We're trying to find this probability that y is greater than 90. Make sure that you can draw yourself a normal curve like we would have in chapter 2, 78.8. We're talking about something like that. How are you going to find that with a norm CDF? Check your answer on the key. Looking over the key, I recognize that the answer for the norm CDF part of it's not there. So I remind you that your lower bound would be 90. Your upper bound would be a bunch of 9s. That is positive infinity with a mean and standard deviation like you calculated, right? A little norm CDF gives us an answer of about 23%. That's a little less than 1 standard deviation above. I expected the answer to be a little bit more than 16%. If you're still not good with the old empirical rule, go back and look at that. How did I get those numbers so quickly? 2, 3, 0, 6. Okay, now the second most important set of formulas for this unit. We have the transformations formulas first. Transformations, taking one thing, multiplying, adding, dividing, subtracting to turn it into another thing. But now we're talking about combinations. Out to the side of this, turn it sideways and write combinations. We're no longer transforming things. We're putting things together. So let's make little squiggles here. These are another thing that's not going to be on your formula sheet. And so these are formulas that you are just going to have to know. The sum and difference for the means of random variables. I'm going to use a couple colors here. I'm going to use green for sum, and I'm going to use magenta for difference here. And hopefully this will be clear enough. If you have, z equals x plus y, the mean of z is going to be the mean of x plus the mean of y. Okay, you're adding 2 random variables together. Listen to this, maybe write it down. The mean of the sum is the sum of the means. Great. The mean of the sum is the sum of the means. And similarly, if we take a difference, z equals x minus y, the mean of the difference is the difference of the means. The mean of z is the mean of x minus the mean of y. Right. So that would have probably been intuitive enough for you. That's for the mean. But now, sum and difference of the variance. Ooh, this is different. So the means is straightforward enough. But now we're talking about the variance. The variance is kind of how far is it away from what we expected? Well, the standard deviation of z, if we're adding the things, well, the standard deviation is going to be, the variance is going to be the variance of x plus the variance of y. You can kind of think of this like what? I don't know, this is how I think of it. Sigma x, sigma y, sigma z. You can think of the standard deviation something like the Pythagorean theorem. Listen with me for a second. The variability in one variable doesn't have anything to do with the variability of this other variable. So their distances from their mean, they don't really have anything to do with each other. They're kind of orthogonal. They're kind of perpendicular, right? They don't add anything to each other. So you can think of variances kind of like kind of like legs on a right triangle. They're independent for some reason. Over here, if we were subtracting the random variables, well, you're still going to add the variances. Sigma x squared still plus sigma y squared. The confusing thing here, the thing that you are not going to like, is that we still add add variances. We add variances even when we're subtracting the variables. We're still going to add the variances. Why does that make sense? Think, you wouldn't have less uncertainty. You've got uncertainty in one thing, you've got uncertainty in another thing. That wouldn't give you less uncertainty. Sigma x, sigma y, sigma z. One thing that you might write down is that uncertainty always adds. Variances always add. We're never going to subtract variances. If there's uncertainty in one thing and uncertainty in another thing, we don't somehow get less uncertainty in the total of those things. Right, so if we wanted to find then the standard deviation, this will be the same for both. The standard deviation of the sum and the difference, sigma z, is just square root sigma x squared plus sigma y squared. And that always works. Regardless of whether we're adding and subtracting x and y, we always add their variances and take the square root to get the standard deviation. And this is one thing that is not on your formula sheet, this stuff that I've outlined in red. It's going to get on a note card. It's very important. You won't see it on your formula sheet. Excuse me. Before finding the sum and difference of standard deviations, before finding the standard deviation of a sum or difference, what conditions must be met? They must be independent random variables. If they're independent, that allows us to kind of think of them as being at right angles to one another. Independence in this idea of variables has something to do with this idea of orthogonality, perpendicularity. And that is kind of weird and beyond the scope of this course to explain why. But if they're independent random variables, we can kind of think about them like this thing has no projection on the other thing. Maybe, I don't know. Yeah. So let's keep on moving. We are going to use that idea of independent random variables. We are going to do a few of these. I don't think I'm going to do all of them. I'm very likely going to leave a few of them for an example video next week. So I'm going to do a couple of them that I'm just going to tell you are going to show up on the test. And the first one that'll show up on multiple choice kinds of questions. This one right here, this Tinder question, it's a multiple choice question. Suppose that the height m of male Tinder users follows a normal distribution. Great. So let's write it up to the side of this. This is a very good MC question. Male users, normal distribution, mean is 68.5, standard deviation of 4. Female users got a height F, normal distribution, mean is 64, standard deviation of 3. So I'm going to write a few things I know down. Males distributed normally, 68.5, standard deviation of 4. I'll use the other color for females here, use the magenta. Distributed normally, 64, standard deviation 3. Okay, so if you're still not comfortable with what I'm writing down, reminder that that is the mean of F and the standard deviation of F. Over here, this is the mean of M and the standard deviation of M. If you're still not comfortable with that notation, please look back to chapter 2. What is the probability that a randomly selected male Tinder user is taller than a randomly selected female Tinder user that he is paired with, or he pairs with, or he matches with? I am sorry if the phrasing is wrong. It has been a moment. So what do we need here? Well, let's write a probability statement. We're looking for the probability that M is greater than F, but how do I do that? That doesn't look like anything I've done yet today. That doesn't look like a combination or transformation. Could I make this a combination or a transformation? It's an inequality. I can move things around in inequalities. I could rewrite this as the probability that M minus F is greater than 0. Oh, M minus F, that could be the thing I work with. We could call that the difference D. So let M minus F equal D, the difference. So now we could say we're trying to find the probability that D is greater than 0. Well, now we just need to figure out, well, what the heck's the mean and standard deviation of D? What's the mean of D? Standard deviation of D. Mean of D is D is M minus F, so the mean of D is the mean of M minus the mean of F, that is 68.5 minus 64 is 4.5. Okay, so the average difference, on average, if I looked at lots and lots of Tinder date differences, average difference in height would be 4.5 inches. Great. Not just one of them, average many of them. Sigma D, what's the standard deviation of the difference in height? Well, there's this much variability in the one height. There's this much variability in the other height. You might recognize that as a Pythagorean triple, 3, 4, 5, square root sigma M squared plus sigma F squared. That is square root of 4 squared plus 3 squared, 16 and 9 make, what is that, 25, square root of 25 is 5. So all of a sudden, we have now decided that D is distributed normally. The average difference in Tinderers' heights is 4.5 inches, that's mu D. And the standard deviation of Tinderers' heights, the difference of Tinderers' heights is 5, that is sigma D. So what could we do? We could say, okay, well, here's D. There's 4.5, and we're looking for what's the probability it's greater than 0. We're looking for that probability. So to find the probability that D is greater than 0, what are we going to do? We have a normal distribution now. Pause it. Try and figure it out for yourself. All right, I looked ahead. We're going to do 2 more examples. I'll probably have something for you next time. The lecture notes completed don't show you how you do this in your calculator. Lower bound 0, upper bound bunch of 9s, mean of 4.5, standard deviation of 5. You get an answer. Aligns pretty well with what we've got in the answer key. 0.8159 matches pretty close what you'd get from the Z table, 0.8160. 0.8159, and we'd get that either with a norm CDF or a Z-score. You'd have to show more work there, obviously. So this apples problem, right next to it, that you're going to see this as a free response question. We're going to wait on it, and I'm going to do one on the next page that looks almost exactly like it, but I'm going to give you another one to save for test practice. You've got how to solve it in the answer key. Save that thing for test practice. Maybe we'll look at it later. The one we're going to look at now is old Mr. Starnes. That's your textbook author. Mr. Starnes and his T. We're going to do this T question. I am probably not going to do this auto dealership question down below. So if you wanted to, you could cross this out and use that area down below for space, because this format is making me crunch things for time. Mr. Starnes, well, Mr. Starnes, likes between 8.5 and 9 grams of sugar in his hot tea. Good, he's a particular man. Suppose the amount of sugar in a randomly selected packet follows a normal distribution with a mean of 2.17, standard deviation 0.08. Great. If he picks 4 packets at random, what's the probability his tea will taste right? So let's define some things. We need to, I know one thing, if, X is amount of sugar in a packet, and I know X is distributed normally with a mean of 2.17, standard deviation 0.08. That would be a good first thing to write down, because I'm going to be putting, sugar packets together. Ultimately, I want to know about the total. I want to know the probability, the total is between 8.5 and 9. So rather, it needs to be a two-sided inequality, probability 8.5 less than total less than 9. This is ultimately what we're looking to find. So we need to talk about then the total amount of sugar. So let's let T represent the total sugar added. And then think about how we're going to write T. This is the big question. Is T, excuse me, the total amount of sugar, T, is it one packet multiplied by 4? Or is it 4 separate packets added together, independent draws? Is it one packet that I multiply by 4, or do I pull out 4 things separately? That's the first thing. And the answer is you pull out 4 things separately. This needs to be X1, X2, X3, X4. This is a combination of 4 independent draws. It's not one packet multiplied by 4. It's 4 separate packets. Where does that make a difference? That makes a difference on the standard deviation formula. So this problem right here is a test question. I'm going to write out to the side test question, and some of y'all are going to be surprised when you see it. Test question. Total sugar, X1 plus X2 plus X3 plus X4. Great. Well, what's the mean then of T going to be? Not surprisingly, it's going to be the mean of X plus the mean of X plus the mean of X plus the mean of X. That is 4 times the mean of X is, what is that? 8.68 grams. Great. And sigma T, however, is not so easy. It is going to be the square root of sigma X squared plus sigma X squared plus sigma X squared plus sigma X squared. That is the square root of 4 times sigma X squared, which will end up being 2 sigma X. What's that going to be? It's going to be 0.16. So all of a sudden, we've established T. T is distributed normally, mean of 8.68, standard deviation 0.16. Have we answered the question? Not at all. I knew what 1 sugar packet gave me. I know now how 4 independent sugar packets sums are distributed, but I still have yet to answer the question about that total. Let's find that down below. We're asked to find the probability then that total is between 8.5 and 9. You could, if you wanted to, and you should, sketch out a quick drawing of this thing. We've got here 8.68 in the middle. We're talking about something a little less than 1 standard deviation below, 8.5, about 2 standard deviations above, that is 9. So we're looking at an area something like that. That's enough work for me. If you've got a probability statement, a statement as to how it's distributed, a picture that shows me that you know what the heck's going on, Looks great. Second distribution, get your VARs menu, norm CDF, lower bound 8.5, upper bound 9. What do we got? 8.68 and 0.16. If you're not doing these in your calculator, I think you're making a mistake. It's just a lot harder if you're doing them on paper. We do that, we get an answer of 8470. So we've got an answer 0.8470. He gets his T right about 85% of the time. Okay. I'm going to do one more example. We've done what have we done here? Let's take a look. We've done a transformation. Let's write that down. This is one thing. This is what I do to your test scores. That's a transformation. We've got a specific combination here. This combination, all right, combo. This is a difference. One minus the other. They love those on multiple choice questions. I'm just telling you, they're going to be on multiple choice. And then I gave you a combination. This was a sum. They love the combination sum. Maybe you're adding sugar packets or apples, or who the hell knows, you're adding some things together, seeing if it reaches some total. That's an FRQ question. So I'm going to write FRQ here. Got one more question for you, and it's kind of a combination of everything. A challenge for an upcoming concert. Each customer may purchase up to 3 child tickets and 3 adult tickets. Let C be the number of child tickets purchased by a single customer. This is our last example of the day. Compute the mean and standard deviation of C. Okay, great. Let's pause, calculate the mean and standard deviation of C. Multiply that out real quick. Multiplying the values times their probabilities. That's 0, that's 0.3, that's 0.4, and that's 0.3. That adds up to 1. So the mean number of children's tickets sold is 1. Great. It is that easy. Suppose the mean and standard deviation of the number of adult tickets is 2 and 1.2 respectively. Assume the number of child tickets and adult tickets purchased are independent random variables. Seems suspect, but we need that for the formulas to work. Compute the mean and standard deviation of the total number of adult and child tickets purchased by a single customer. All right, so now we've got this B thing. B is the total number of tickets, is the number of adult tickets plus the number of child tickets. All right, well, we've got formulas for those. The mean of T then is going to be the mean of A plus the mean of C. And standard deviation of T is going to be square root sigma A squared plus sigma T squared. Let's go through the work finding those. I recognize that I failed to calculate that the standard deviation of C up above was 1. They're both 1, and you needed that to do this calculation down below, 1.2 squared plus 1 squared. The mean number of tickets sold total is 3. Standard deviation, square root 1.2 squared plus 1 squared. What are we going to get there? Square root 1.2 squared plus 1. You can square 1, it doesn't change it, is 1.56. So that's the mean and standard deviation and total number of tickets sold. And then part C asks us, suppose each child ticket is 15 and an adult ticket is 25. Compute the mean and standard deviation of the total amount spent. Oh my gosh. So now we have S is the total amount spent. We spend $25 on an adult ticket and $15 on a child ticket. We need to transform and combine. We're going to transform first. We're going to combine second. So what does that mean? That means the mean of S is going to be 25 times the mean of A plus 15 times the mean of C. Well, that's 25 times 2 plus 15 times 1 is going to be 65. Standard deviation of S, well, normally we would add the squares, but we've got to multiply by 25 too. So we're going to do that 25 sigma A squared plus 15 sigma C squared. When you do that, that becomes 25 times 1.2 quantity squared plus 15 times 1 quantity squared. When you do all that in your calculator, square root 25 times 1.2 squared plus, what do we say, 15 times 1 squared, 33.54. Let's put some dollar signs on those so we remember to ourselves that that's the average amount of money that a couple of people spend when they come to this thing, or this family spends, and that's the standard deviation, the average difference from that mean value. You've got four examples here. We are going to certainly need to come back and do some of these other ones, but that's going to be closer to test time or maybe before our 6-3 quiz sometime next week. So we will wrap it up here. How long have I taken? 35 minutes. That's not bad. We will see you next time.